Bonjour, welcome to Wahsa Distance Education Center's radio Zoom classes. This is SVN3E, Grade 11 Workplace Science, and I'm the teacher, Bronwyn Slate. If you'd like to participate live today, you can call the Wahsa studio at 1-800-465-7144 or 737-4017. You can listen on the radio at 91.9 FM and also on the television at Bell Express View Channel 972. You are always welcome to join me live through the Zoom link, which is available from me, your teacher, and also your DEC. Our classes are scheduled from Monday through Thursdays from 10 to 11 in the morning, and we are in our first week of our 9-week course. Though it is early, it's still important to know what you will be needing to submit once the time comes. So the key questions are in your IL package that you received from us, and they are all the questions to submit for marking. So they're listed at the end of each of your IL lessons. Sometimes there isn't a lot more information in that. Mostly it's just in the workbook that we sent you. But you need to do all the questions. So the check your understanding questions, sometimes there's activity questions, and also the review questions. Please show all of your work, your steps, and your thinking. So explain all of your thoughts, opposed to just giving me one word or something like that. Give me complete sentences, explain all of your thought, and make sure you're actually answering what the question is asking. You can do this by hand or electronically. You are welcome to write in the workbook if you'd like. It is yours, though it's a small space, so it might not set you up for success if you do write in that workbook. If you're going to do it electronically, Word and Google Doc files are the easiest for me to access. If everyone has access to Google Docs through your NNEC email account, so you can access that for free, just let me know if you're not sure how to do that, and I can help you walk through that. If you're going to use a different file type, that's most likely fine. Just let me know so that we can figure out to make sure that I can actually open your files. We don't want you to do a whole bunch of work and then for some reason I can't open your files. So just communicate with me so that we can make sure I can access all of your information. All right, so then how can you submit your work for marking? If you are going to do it out by hand and you want to scan it, you can do that and then send electronically, or you can just send it electronically if you do it electronically. So to scan your completed work, you can use a Apple device. There's the Notes app in your is one of your applications that comes with the device, and the Android devices have a Google Drive app that comes with it. Both are free. You can download them and are fairly straightforward to scan. If you scan your work opposed to taking pictures, the files are just a little bit smaller and more uh, condensed so that I get them as one file. So it's a little bit easier for me and possibly for you. But if you need to take pictures, that's also totally fine. No worries at all. Then you can send it to me either through email to studentwork@nnec.on.ca and CC it to me, bronwyn.slate@nnec.on.ca, or you can send it to me through Facebook Messenger to bslate.wahsa. The second method is to drop your work off directly into Lookout if you're in town. We have an outdoor mailbox at our 74 Front Street location. We're the bright red building next to the post office, and we have a small white mailbox next to our side entrance. We are not yet open to the public, hopefully soon, but for now, just putting your work in that mailbox, and I will get it shortly and get it back to you as soon as I can. The third method is to hand your work into your DEC. Your DC can either send your work through the Express or fax it to 807-737-1732 or toll-free fax to 1-800-463-7852. You are also welcome to fax if you have access to a fax machine. That's totally fine. If you'd like to connect with me through social media, both my YouTube and my Facebook are under the name bslate.wahsa. Sorry, brain's not working for a second. You can friend me on Facebook and subscribe to my YouTube channel, and then you get notifications every time I upload a new video. All of our radio Zoom classes are recorded, and I post them to YouTube in a playlist called SVN3E, and I share that on Facebook so that you have access to all of our lessons to review them at a later date if you'd like. I also post supplementary videos, the videos that we watch in class. I link them into a playlist on YouTube. So you can access them so that you can watch the full ones if we don't have a chance to watch them all in class. They're all the ones that are YouTube affiliated are there as well. Science is a really visual subject. I try to connect as many images and videos and diagrams as possible, charts, things like that, to really get us a full understanding of what's going on in our science course. So I strongly encourage you to connect with the visuals if you are able. If for some reason you don't have access to reliable internet, or you can't join us live through Zoom and you can't access the YouTube videos, let me know and I can send you a copy of our recordings so that you can still get as much information as possible, even if you can't access them because the internet is spotty, which happens to all of us. So if you have any questions or concerns, please reach out to me. My email address is bronwyn.slate@nnec.on.ca, and my Facebook is bslatewahsa. You can call me at the office at 807-737-1488. My extension is 2209. And you can call me toll free as well at 1-800-667-3703. My office hours are Monday through Friday, 8 a.m. to 2 p.m., though I teach from 9 till 11. So if you call me during that time, you'll need to leave me a message and I'll get back to you as soon as I can. I think it's important to position myself as an educator within the context of this course. I have white settler ancestry, I have white privilege, and that means that the way that I walk on the world is easier than many other folks. I recognize this, and though I can't change it, I try to acknowledge it and adjust accordingly as best as I can. I do live in Northwestern Ontario on the traditional territories of the Anishinaabe people and work to honor and learn from the cultures and the rich wealth, vast knowledge that is here. But as an educator, I have lots to learn and unlearn. I'm always working to improve and to do better, and particularly within social justice concepts and ideas, and recognizing other people's experiences and trying to integrate that into the way that I teach, as I know the way that I learned and the way that I've experienced education is different and, again, easier than many other folks. And so I think that's really important for me to do that work in order to make it better for people who do not have white privilege and who struggle with oppression and discrimination within their lives. Our textbook also, I realize, is Eurocentric. So the experiences, the understanding is based on a European value system, and which most of Canada is based on as well, being a colony of European countries. So I realized that it does often ignore Indigenous, Inuit, and Métis, both their knowledges and experiences of these people. So I'm working towards finding another resource that maybe integrates Indigenous, Inuit, and Métis knowledges and experiences more and makes it more representative of the wealth of information and knowledge that is in our communities. But that's something that I've yet to find. If anyone has any suggestions or ideas, I'm happy to hear. But I try to integrate when I can what I know about these folks' experiences and knowledges when I can. Again, something that I'm working on and improving upon, and happy to hear feedback. And if anyone has any suggestions or offer of support in order how I can do better, I'm happy to hear that, and we'll work towards to always improve. All right, so we are in Unit 1 officially. We are, this is part of the We Are the Guardians of Earth Spheres unit, is Unit 1. And it talks about how Earth is a superorganism. So all the living and non-living parts keep Earth healthy. All of Earth's spheres, the land, the air, and the water, are connected to one another, to us, and all to other life forms. So in this unit, we will be learning how Earth spheres, about those spheres, and how people affect them. So in lesson 1, the components of soil, water, and air, first we're learning just directly about what these spheres are um, that make up our Earth. So our learning goals are that at the end of this lesson, you'll be able to identify and describe components of soil, water, and air. The success criteria, so how we know that we've achieved this, is that you can explain the components of soil and the impacts of porosity. You can describe the water cycle as well as how acidic and basic solutions work. You can explain what gases make up the air and their importance to living things. So first we're going to start with soil. What is soil? So soil are a complex mixture of minerals, water, air, organic matter, and various decaying organisms. So often people might just think soil is dirt, and yes, it is dirt, but that what actually makes up that dirt, makes up that soil, are all of these other parts. So ideally, soil has a large mineral content, so those are the rock particles. It's about 45%. And then we have 25% air and 25% water, and then 5% organic matter, which are the decaying organisms and potential and living organisms as well. So soil forms the surface of our land. It is the skin of our earth. Soil is capable of supporting plant life and is vital to life on earth. It's sort of the foundation, both in terms of what we stand upon, what we build upon, but also the foundation of our survival in terms of our air and our food, and how water is purified. Soil is essential to all of that. So what's organic matter? Air, water, minerals are pretty basic, but what is organic matter? So this contains plant, animal tissue, bacteria, fungi. So when you're looking at soil, there's a lot more than just going on than just grains of little broken up rocks. We have humus, which is where the organic matter is very well rotted and decayed, and it results in a fine, crumbly, dark dirt. So this is a good example of humus, which is usually the top surface of our soil. It helps soil to hold water, which gives plants nitrogen, phosphorus, and potassium, which are all minerals that plants need to grow. So we're going to watch a video about about soil, just to sort of get an understanding of what's going on there.
Air is present in the soil, just as there are animals that live in water. There are also animals that live under the surface of the soil. These animals also require air to live. The following activity demonstrates the presence of air in the soil. Dig out a small lump of soil from your garden. Place this lump of soil in a small vessel. Pour a small amount of water on it. Bubbles are observed coming out of the soil. This is because the water molecules displace the air present between the soil particles, and the air rises and escapes from the surface as bubbles. This air is utilized by the organisms living in the soil, such as ants, beetles, and earthworms, to respire. The animals that live under the soil make deep holes and burrows in order to facilitate the free flow of air within the soil. Earthworms are especially popular in this aspect and are known as farmers' friends, since they keep the different layers of soil under continuous rotation, thereby keeping the soil fertile. It has been observed that a lot of worms and animals that live inside the soil come out during the rainy season. This is because the water from the rain displaces the animals in the soil, making it hard for the animals to respire. Soil is thoroughly ploughed before the cultivation of crops, so that there is always a steady flow of nutrients water, and air.
All right, so that video shows us just how the air and water is interconnected within the soil. So that works really well to just understand how all those parts are really important to the soil. Also, whenever they say respire, they mean it's breathing, just to make sure that's language that we might not necessarily use in everyday life. All right, so then what is going on with minerals within soil? So minerals are small rock pieces, and their particles are broken up over thousands of years. This happens through ice, rain, wind, and other natural forces that breaks rocks up into smaller parts. So it contains rock pieces are defined by size. So we have sand, which is between 2 and 0.05 millimeters. So those are the biggest pieces, are the sand. You can see here in the diagram the larger grains you can see. Silt, which is when the pieces are between 0.05 and 0.002 millimeters, so getting finer. This is a picture of silt. You can still sort of see the grains, but they're definitely finer than the sand grains. And then clay, which is when the particles are less than 0.002 millimeters. And remember, like, a millimeter is small. If you think about a ruler, a millimeter is really small. And so these are tiny particles that are not really easy to see just through our own eyesight. So sand creates porous spaces. So because the bigger grains don't fit together so well, it means that they help with that, allowing for there to be room for air and water in the soil. And the silt and the clay provide nutrients. So they're generally made up of phosphorus, potassium, sulfur, magnesium, boron, zinc, things like that are all minerals that are all needed for plants to grow. So then porosity is the pore space in the soil. So how much space there is between the grains of soil. The pore spores contain air and water, which contain gases like oxygen. So the effect on plants are that if there's no oxygen, plants die. They need the oxygen. So if there's no spaces, if there's non-porous, non-permeable, there's no pore spaces. Here on this far left side of this diagram, you can see all of the grains of soil are completely together. There's no places between them. So that's like really heavy clay, lots and lots of clay particles. Then plants can't get any oxygen. There's also no space for water. So then plants can't grow. And then if there's no, on the other side, if there's no nutrients, because there's just lots of spaces, then plants die because the plants need nutrients. So plants need water, oxygen, and nutrients in order to thrive. So plants both need so on this connected pore spaces, this side, the right side, where it's really porous, really permeable, the water is just going to run through this soil. So it's just going to go really fast and it's going to take away the nutrients and wash it away. Whereas here in between, where they're in the middle of this, where there's unconnected pore spaces, this is porous but non-permeable. So there does have porous spaces, but you can't just flow through it. The air and oxygen are going to get trapped, which means the nutrients are still going to be present. And then this is the best sort of soil for plants to grow. So both your porosity being too high or too low is not good for plant growth. And this is how we measure the health and how good a soil is for growing different types of plants. So here is another video to compare the sandy soil and clay and loam soil, which is like silt, sort of a combination is loam soil.
Soil is formed from the breakdown of rocks and minerals on the Earth's surface through weathering and erosion. Soil is important for growth and life of plants. It helps hold the plants straight up and a source of nutrients and water which the plant uses for growth and living. Let us learn more about the three types of soil. Sandy soil consists of small particles of weathered rocks. It has the largest particles among the three types of soil. Its texture is rough. Drainage system and aeration are good. However, it has low nutrients and poor water holding capacity. Clay soil. It has the smallest particles among the three types of soil. Its texture is fine and rich in nutrients which plants need. The soil particles are tightly packed with very little or no air space. The soil has very good water holding capacity. Clay is the densest and heaviest type of soil which does not drain well. Loam soil. It is a combination of sand, silt, and clay. Its texture is rather fine. It's black or brown because of a high amount of humus. It has the ability to retain moisture and nutrients. In this experiment, we will test the water flow and absorption in each type of soil. I prepared 3 cups with holes at the bottom. The water is measured and the timer is set. I am expecting little amount of water for the clay soil, but it turns out to be the opposite. Why? Based on my observation, the clay soil is already wet. Therefore, it will not absorb much water. Also, the water made its way on the sides of the plastic cup, not through the soil. On the other hand, sandy soil is dry, so it absorbs some water. Also, as expected, the water passed through the sand real fast. Loam soil is also dry. It absorbs more water than sandy soil. Some water passed through the soil and was captured by the cup at the bottom. Let us do part 2. This time, all the 3 types of soil are wet. For the results, sandy soil and clay soil did not absorb water anymore, while loam soil absorbs 5 ml of water.
All right, so that just shows you how different types of soil react with water, which also represents the air that is inside of those types of soil, because the water replaces the air. Okay, so that gives us a little bit of understanding how soil is made up. Now we're going to look at water. So we want to have a little bit of an understanding of vocabulary with water. So this is really vocabulary that's all of scientists, all of matter is made up of, and we're going to use it in order to help us understand some elements of water. So first, an atom is the smallest part of matter. So of everything is made up of atoms. It is the smallest thing that exists. And then we have elements, which is matter that is made up from only one type of atom. So we've heard already about nitrogen, phosphorus, calcium, sodium, hydrogen, oxygen. These are all elements. Then a compound is when you have 2 or more different elements combined or bound together. So you may have heard of H2O, which is 2 hydrogen atoms and oxygen atom combined together, and that makes water. So having the oxygen and the hydrogen together makes water. So now we have something new, a compound. So then looking at the structure of an atom, which is the smallest part of matter, but it's made up of smaller things. So we have the nucleus, which is the center of your atom, which is here, which has a group of neutrons and protons in the center. So a neutron, which is found inside the nucleus, is an uncharged part of an atom. It is not positive or negative, it's just neutral. Then we have electrons, and electrons are negative parts of the atom, and they orbit the nucleus. They fly around outside of the nucleus, and they're negatively charged, as I said. And then a proton is positively charged particle of the atom, and it's found again inside of the nucleus with the neutron. The number of each of those things, that defines what type of atom, what type of element it is. So here's another diagram where you can just see the nucleus is this space here, and the neutrons and protons are inside and the electrons are outside. All right, so this all relates to some more vocabulary, which there's a solvent. So this is a substance that can dissolve another substance, is what a solvent is. An ion is when you have an electrically charged particle. So it's either a positive or a negative charged particle. Ionization is when an atom gains or loses an electron, and that changes the charge on that atom now. It's either positive or negative, depending on if it gained one or lost one. So when you have a solvent, it pulls, what's happening with a solvent is that it is pulling the ions away from your substance and changing it and dissolving it. So water is, these red ones and white ones are 2 hydrogens and an oxygen, and they are pulling the positives and the negatives away, which is why we're talking about solvents and water. So water is what's called the universal solvent. So it's because it dissolves so many substances. It is able to, it has a little bit of a positive charge and a little bit of a negative charge. And so it's able to pull apart lots of different substances. So here's another diagram. You can see we have your oxygen and your hydrogen, and it's going to pull apart this substance here. So we're going to watch a video.
As I'm in the midst of applying for residency right now, wish me luck, Grammarly has again been a lifesaver with my application.
Hello?
So video talks about why water is called the universal solvent.
In this video, I'm going to teach you about water and its role as the universal solvent. In the process, I'm also going to show you how polar solvents rip apart polar solutes when they dissolve. First, let's remember a few things. 4 things specifically. First, water is polar, and that means that its molecules act like little magnets with positive and negative ends. Second, a solute is dissolved into a solvent to form a solution. These are the vocabulary words we use to describe the dissolution process. Third, solubility is a measurement of how well one thing dissolves inside another thing. And finally, solubility is high when the solute and the solvent have the same polarity, so they're both polar or they're both nonpolar. Now that we have that review, let's get started. Water is called the universal solvent because it can dissolve an extremely high number of chemicals. Water's polar nature allows it to dissolve almost any other polar molecule inside itself. So water is H2O, the oxygen is partially negative, and the hydrogens are partially positive, so it acts like a little magnet. So we're going to be looking at this process where salt crystals get dissolved into water. We're going to see what happens as the crystals seem to disappear. And we have our salt crystal on the left and the water on the right. So the first thing that I'm going to have you remember is that the salt crystal is not a big block. It's actually made of atoms. Specifically, this salt crystal is made of sodium and chloride atoms stacked together, NaCl, table salt. And to make things easier, I'm going to represent every positive sodium with a big plus sign, and every negative chloride with a big minus sign. This works the same way for every sort of polar or electrically charged molecule that water dissolves. So, let's say that in the random course of movement, one of these water molecules moves in towards the salt crystal. Now the oxygen is a little bit negative, and the hydrogen is a little bit positive because water is polar, so it acts like a little magnet. And magnets attract each other. Specifically, the opposites will attract. So that means that this negative end of this water molecule will attract this positive atom in the crystal. So when they're attracting, the water molecules are still moving around, it's a liquid, and so when it moves away, it drags this particle with it. And so the salt crystal now is missing a piece, and that sodium, that positive atom, is now dissolved into the water. And remember, it's not really a magnet, it's a water molecule. So the same thing can happen. A water molecule moves in, but this time the hydrogens are close to it. And remember, the oxygen is negative and the hydrogens are positive. So the positive hydrogen is going to connect with the negative chloride, or whatever the negative atom is in that compound. So once the positive and negative are stuck together, then when the water molecule moves away, it'll drag it with it. And so the salt crystal is now missing another piece. And so this is just going to keep happening. Water molecule is going to get close to the crystal, take either the positive or the negative atom, and take it with it as it moves away, until eventually the entire salt crystal is gone, and its pieces are spread out among the water molecules. This is a way to visualize it too. You have sodiums and chlorides, or any two atoms, that are electrically charged, and the water molecules come in, grab parts of it because it's polar, and rips them off until eventually there's nothing left and it gets spread out in the water, which is what we call dissolved. Water is called the universal solvent because the solubility of almost all polar chemicals is extremely high in water. Water can dissolve almost any polar thing. This is because the polar nature of water allows it to rip apart the electrically charged atoms in these chemicals. There are a lot of things that water doesn't dissolve, mostly nonpolar things like Sharpie ink or rubber, but we still call it the universal solvent because it's really commonly used and it dissolves a lot of stuff. I don't like this name very much, but it is very common. Anyway, that was it. I hope that was helpful.
Lucidchart makes intelligent diagramming easy and helps your best ideas become real.
So that video showed us a little bit about how universal solvent, water, works to dissolve other substances. So now we're going to look briefly at the water cycle to help remember how water cycles around our environments. So we have surface water, which is water on land, so our ponds, lakes, rivers. You have groundwater, which is water in the soil or on rock below the Earth's surface. Then we have evaporation, which is when water is heated and it moves from land and surface water to the air and becomes water vapor. And we have precipitation, which is when water vapor cools and creates clouds and then falls as rain, snow, sleet, things like that. And then we have runoff, which is when precipitation falls onto the land and then flows onto the surface to lakes, rivers, and oceans. When we have percolation, which is when the surface water moves into the ground. So here is a diagram that shows this, as opposed to just having the language, but that defines all these words. There's a few other words on here that don't worry about. They are part of the water cycle, but they are a little bit more than we need to understand. So thinking about, we have our surface water and our groundwater, right? And so the surface water can be evaporated, heated and evaporated into clouds, or the groundwater can move underground to surface water, so through the ocean, or it can come up to a pond or a lake, and then it evaporates off of the water surface. So water evaporates both off water and land, and then it condenses as it cools, condenses into clouds, and then precipitates either through rain, snow, sleet, various precipitation. And then it either collects directly into our surface water, or it runs off of the ground into a surface water, or it infiltrates through the ground or through the surface water into the groundwater through percolation, and then cycles back through. So this is how our water is reused and recycled again and again, but why it takes time. So this is why we have to think about water, yes, is renewable, but it takes time for this whole process to go through. And now we need to think about acidic and basic solutions. This is something else that's going to come up throughout our course in terms of water. So acids are substances that produce hydrogen ions when dissolved in water. So water is, remember, H2O, and when the substance is in water, we end up with just hydrogen ions that are pulled away from our water ions. The more hydrogen ions in the water, or in the substance, the more acidic it is. This tastes sour. It has strong acids can corrode, so damage or eat away metal and other substances. And it can cause severe skin damage that feels like a burn. Vinegar is a common acid, or like lemon juice is another one that you might be familiar with. So then we have a base. And so base is a substance that produces hydrogen oxide ions. So we take away that one hydrogen and we're left with an oxygen and a hydrogen when they're dissolved in water. So that's what gets left behind, this negatively charged ion. So again, the more hydrogen oxide ions, the more basic or alkaline. It tastes soapy or bitter. Not that I'm encouraging you to taste these things. Strong bases are caustic, so again, damage and eat away to organic substances. It can still feel like severe skin damage. It can still be like a burn on your skin. So both acidic and basic solutions are generally not safe to touch if you're the really strong ones. And baking soda is a common base that we are familiar with. So then we have the pH scale, which you may have heard of before, which is pH stands for the power of hydrogen. And the pH scale measures the acidity or the alkaline or basicness of a substance. So water is neutral. It has 7, so it is neither acidic or alkaline. It is in the middle. And then as we get more and more, as our numbers get smaller and smaller, closer to 0, our substances are more acidic. And as we get higher, closer to 14, our substances are more basic or alkaline. So now you can answer the key questions on page 6, the check your understanding questions 1 through 3. We've covered all of those topics. All right, and then looking at air. So air is a mixture of gases. We have nitrogen, oxygen, water vapor, carbon dioxide. You can see here various gases. Nitrogen is what makes up the most of our air. Carbon dioxide and oxygen are essential for plants and animals to live. The carbon cycle explains how the gases move within our Earth spheres. So we're going to play a quick video.
Welcome to Moo Math and Science in the carbon cycle. Carbon is an element that is vital to most living organisms on Earth. It is also a key component of our atmosphere. Carbon has the ability to cycle through our Earth, the ocean, living factors, abiotic factors, and the air. The carbon recycles among 5 major locations. These items include the atmosphere, the terrestrial biosphere or land, the Earth's interior, the ocean, and human influence. Let's take a look at what happens at each of these areas. Carbon is found in the atmosphere in at least 2 forms, carbon dioxide and methane. This atmospheric carbon can be absorbed by autotrophs like plants and plankton to be used for photosynthesis. It can also be absorbed by bodies of water and the ocean. When carbon is absorbed by the ocean, it reacts with the water and creates carbonic acid. The terrestrial biosphere, which is another term for the Earth's land, has several paths of carbon that it can take. First, there is an exchange between plants and animals. Plants absorb carbon in the form of carbon dioxide for photosynthesis, and animals release carbon dioxide during cellular respiration. Also, heterotrophs eat plants that contain carbon. Animals also release carbon as methane during digestion, and the soil contains decomposers that release carbon into the atmosphere and the soil. Carbon is also stored in the Earth's interior. Carbon in the lithosphere includes fossil fuels like coal, oil, and natural gas, along with deposits like limestone, and volcanoes may release some of this carbon stored in the lithosphere when they erupt. Up next, the ocean. The ocean has the greatest exchange quantity of cycled carbon and stores a large amount of carbon. The ocean absorbs carbon in the form of carbon dioxide. The ocean also has a large amount of plankton that absorbs carbon dioxide that it uses for photosynthesis. Humans also influence the movement of carbon. Humans burn fossil fuel, which releases carbon dioxide into the atmosphere. Also, the production of clinker, which is used for cement from limestone, also releases carbon. In addition, deforestation from humans can cause the amount of carbon in the atmosphere to increase. So there you go, an overview of the path of an atom of carbon that may take place during the carbon cycle. Thanks for watching, and Moo Math uploads a new math and science video every day. Please subscribe and share.
All right, so that just gives us an understanding of how carbon cycles through our environments as well. And then nitrogen also cycles through. So living things also need nitrogen, but few organisms can get it directly from the air. So the nitrogen cycle explains how the large amount of nitrogen that's in the air, remember, it was mostly nitrogen, becomes usable by living things, because many of it, we can't breathe in nitrogen and use it. So once again, here's another video, our last video of the day, I believe, which is the nitrogen cycle.
Welcome to Moo Math and Science. In this video, I'd like to talk about the nitrogen cycle. Our atmosphere is made up of 78% nitrogen. We need the nitrogen for our DNA and for proteins, but we just can't breathe in the nitrogen like oxygen, but we must absorb our nitrogen in our food. Nitrogen follows a cycle where it travels from the atmosphere to the soil, to animals, and back, and in a cycle. Nitrogen in the atmosphere falls to the earth by precipitation, such as rain or snow. Once in the soil, it finds its way to bacteria on the roots of plants. At the roots, the nitrogen is combined with hydrogen to make ammonia in a process called nitrogen fixation. Lightning in the atmosphere can also do this. Now, ammonia is toxic, so additional bacteria combines this ammonia with oxygen in a process called nitrification. At this point, the nitrogen is in a form called nitrite. Additional nitrifying bacteria convert this nitrite to nitrate. At this point, plants can absorb this nitrogen in a process called assimilation. However, not all of the nitrate is absorbed, but some of it goes to the bacteria that release the nitrogen to the atmosphere in a process called denitrifying. The nitrogen returns to the atmosphere. Also, once in the animal, after it eats the plants, the animal either dies or needs to get rid of waste. Another type of bacteria then takes this and along with decomposers and breaks this nitrogen either in the waste or the dead animal, and by a process called ammonification, the nitrogen can enter the cycle once again at nitrification, and the cycle continues. I hope that helps with the nitrogen cycle, which is how nitrogen keeps recycling itself. And remember, Moo Math uploads new math.
All right, so again, that shows us how nitrogen is cycled through. There's a lot of big words in there. We don't need to know all of those. That's fine, but it just helps us understand what is going on with the nitrogen cycle as well, and how we get nitrogen even because it's in our air, but how there needs to go through processes in order for us to actually be able to use it. So now you can answer the questions on page 7, the check your understand questions 1 and 2. All right, so we've covered our lesson 1 completely. So let's go through the highlights of what we've done today. So we've talked about the components of soil, water, and air. So soil is made up of air, water, minerals, and organic materials. The mineral composition, the sand, silt, and clay affects the porosity, which then affects how things can grow in that soil. Water is a universal solvent, and which is key to acid bases, and which was measured through the pH scale. And the water cycle shows us how to understand how water cycles through our systems and becomes refreshed. And then we talked about air and how it's made up of various gases, mostly nitrogen, but how we get the carbon and the oxygen and the nitrogen from our air to use, which plants and animals all need in order to thrive and survive. So hopefully you now feel comfortable with the success criteria of today. So can you explain the components of soil and the impacts of porosity? Can you describe the water cycle and as well as how basics and acidic solutions work? And can you explain what gases make up the air and their importance to the living things, how all that works and cycles through our system? So now you can do the key questions on page 9, which are all review questions. So they are the questions 1 through 12. Again, you can write in your book, but if you look at the screen, you can see that these spaces are fairly small and really don't necessarily set you up for success. So I'd encourage you to either write it on another piece of paper or type it up on a document as well. That might be better for you. As always, if you have any questions, please reach out. And this, I know today's information is hard to connect necessarily to why it might matter to you, but these are building blocks, understanding how the Earth atmospheres work, or the spheres work, how the soil, water, and air are interconnected, helps us understand the impacts that we have on them as we go. So first, we're just learning about the basics of the environment so that we can then talk about how humans impact them and what are the repercussions. So if you want to chat about anything, please reach out. You can call me at the office at 807-737-1488, extension 2209, or also call toll free at 1-800-667-3703. You can email me at bronwyn.slate, and that's spelled BRONWYN.SLATE at nnec.on.ca. You can connect with me through Facebook at Slate Wahsa. And remember, YouTube is also Slate Wahsa, where a recording of this lesson and all of the links to the supplementary videos, as well as directly the supplementary videos, will be up there as well. My office hours are Monday through Friday, 8 a.m. to 2 p.m. So reach out and connect if you need some support. Thank you so much for joining me today. I hope you have a lovely day. Mogwitch.